שלוש, היא שלוש.
נכון, אבל לא יודע, זה יכול להיות לא אחד או מינוס אחד, כאילו זה יכול להיות לא אחד, נכון, אז כן מכניסים מה שנסתברו אותה.
כן, בוודאי. קודם כל מבחינת הרצון, זה לא משנה לי איזה מהם זה יהיה, של אחד, יהיה אחת פי אחד, לא משנה איזה.
נכון, זה בטוח אחד.
זה גם ככה, כן. איך שאני הגדרתי את זה בינתיים, אז יש לך יכול להיות שזה טעות וכדאי להגדיר את זה, אבל בינתיים הגדרנו את זה ככה. עכשיו כשאני עושה את התחום הזה, בלי אפילו לכתוב את האחרית אני פשוט מפריד, אני חושב J שווה ואז עכשיו יש את התחום שהייתי צריך לפרק אותו המינויים, יש לי פה דלטה מינוי כל סיפור פה אני רוצה שחצי סיפור
גם באיברים, אותו דבר באיבר ששווה לעצמו, זה לא יתקבל, אז יש לי לבחור.
כן, רק ב-I שווה J יש שם משהו לא יתקבל. אתה יכול להוציא אותו, זה יכול עכשיו.
הדלתא לא מוסיפה לי הסתברות, אתה אומר ככה, אז אני יכול להתקשר ולהבין את זה, אני עשיתי את זה ככה ועשה לי...
לא, כן, מכניס לך פה הסתברות, AI אפשר להתייחס עכשיו... כן, Before Jonathan starts, there was a request to delay the submission of exercise 5 because all the LSAT students have to submit something next week. So I'm going to delay the submission until Tuesday of the following week. But I reserve the right. I might put up the next exercise already before then. I might think of it in my head as if the submission deadline was the same as it originally meant to be, and if I am ready to, then post the next exercise.
Just bring the microphone to here. So the question that we are addressing today is the effect of the bounded nature of synapses on the ability to store a large number of memories. Now, in principle, there are various ways of storing memories, and one can ask different questions. For example, one can ask a question: given that you have access to all past memories again and again and again, what would be the largest number of memory patterns that can be stored? This is one kind of a question. It falls in a framework that is known as batch learning. But we're asking a different question here. And the question is the following. Let's assume that memories arrive one after the other, as they do in real life. And every time that a memory arrives, there is a change in the efficacies of synapses. In this framework, how many memories can we store? So the Hopfield model was a way of implementing this idea, but without the boundedness of synapses. And we are interested in bounded synapses because synapses are well bounded. And to the extent that some people believe, I'm not one of them, but some people believe that synapses are in fact binary. They can attain two states, potentiated and non-potentiated, and all the LTP that you see in experiments, well, typically you see jump, but if you repeat the stimulus and you see a graded response, all this graded response is a result of averaging over many synapses. Some were potentiated and some were not. And there was a heated debate in the literature about a decade ago about this question of whether synapses are binary or not binary. It has not been fully resolved, but I think it's clear to everyone that synapses cannot attain an infinite number of states. Now, if synapses cannot attain an infinite number of states, then they can attain, well, a finite number of states, right? So this would be the number of this finite number of states that the synapse can attain, and the synapse starts from one state. Let's say it starts from this state, and there's a new memory pattern, and there's potentiation, then potentiation again, and maybe depression, and so on and so forth. And the framework, one framework to look at these changes is a framework of Markov chains. And now you already know that Markov chains converge exponentially fast to a stationary distribution. Now, if they converge exponentially fast to a stationary distribution, this implies that the memory trace is lost exponentially fast. So even without going into the details, we immediately understand that there is a problem here. And this problem is the topic of today's class. Questions? So let's remind ourselves the general framework. So what you did, what we started together and continued on Sunday, is the probability distribution over the state at some time t is equal to n will be equal to m to the power of n, where m is a transition matrix, times the distribution over the states at time 0. And then we move to studying this simple problem of a drunk moving in a house with a finite number of rooms, and we computed m and discuss its properties. But now we go back and think about our synapses. So what we did, thinking about synapses, was to construct what we called a signal And this signal is, we defined it as 1 over n, where n is the number of synapses in the network, times the signal due to potentiated synapses. So we're summing over all these synapses that were potentiated given a particular memory pattern. And we see how different they are from the average over the synapses. And we subtract those synapses that were depressed. So this is what we called our signal. And a necessary condition for a memory to be maintained is that this signal will be larger than what? Zero is a necessary, but we can refine it. It should be larger than something larger than 0. I'll explain why. So let's say that you randomly choose a subset of synapses in a network that was not exposed to this memory pattern, and you compute this quantity, and then you compute this quantity. What do you expect the value of this to be? Will it be positive, negative? In a network that didn't learn anything, will it be positive, negative, 0? What do we expect? If we randomly select synapses. Sorry? Well, there will be a distribution. Whether or not it will be uniform, we expect, well, it will not be, distribution over values is not, cannot be uniform. But it is true that it's unlikely that this signal will be equal to 0. It will either be positive or negative. We expect it in 50% of the cases to be positive and in 50% of the cases to be negative. So being positive enough is not sufficient. We want it to be larger than a random, what we expect from a random subset of synapses. So this is a requirement. Well, by the way, if we consider the Hopfield model, the standard Hopfield model, what will be the signal in the Hopfield model? If we take the Hopfield model, what would be the signal in the Hopfield model? So let's think about the Hopfield model as something sequential. Every time that we add a memory pattern, we make a change, which is a change in Jij, which will be equal to 1 over n pi pj, the product of pre and postsynaptic activities. What would be the signal then? I'll remind you the Hopfield model. Jij is equal to 1 over n sum over mu pi mu pj mu. And we can write it also as a learning rule, the change in Jij, delta Jij, at time mu is equal to 1 over n pi mu pj mu. So every time that we present a memory pattern, there is a change that is equal to 1 over n product of pi mu pj mu. So what is the signal in the case of the Hopfield model? Do you need coffee? Anyone? Every time a new memory pattern appears, what happens to the synapses? Some synapses potentiate and some synapses depress, right? What is the fraction of synapses that is potentiated? What's the number of synapses that is potentiated? What is the number of synapses that is depressed? Half of the synapses are potentiated and half of them are depressed, approximately. How many synapses are there in a network of n neurons? N square. So we know that half n square will potentiate and half n square will depress, right? By how much do they potentiate and depress? 1 over n. So in the standard Hopfield model, the signal will be 1 over how many synapses are there? We said n squared. Times how many are potentiated? Half. So we have n squared over 2 times the magnitude of potentiation, which is 1 over n, minus n squared over 2, those are the ones that are depressed, times minus 1 over n, which is equal to 1 over n. So the signal in the Hopfield model, is 1 over n. What would be the magnitude of this quantity by chance? So let's say that we have a Hopfield model with one memory pattern, just one memory pattern. And we consider this quantity. What would be the magnitude of this? So in the Hopfield model with one memory pattern, so what we're interested in is the variance of 1 over n out of what? So we randomly select half of the neurons and we consider their value, sum over the values. We randomly select half of the neuron and consider sum of the values. We subtract these two numbers. So this is like sum over n squared elements. Each one is plus or minus 1 over n with a probability 1/2. So the variance of this would be what? I leave it to you as an exercise. Let's move on. Okay. So this is a Hopfield model, but the Hopfield model is not bounded. Now we're thinking about a bounded problem, and we can also consider other learning rules. We can consider learning rules in which potentiation and depression don't occur with a probability 1/2, but with different probabilities. So we will consider a general problem. So now what I'm plotting, these are not neurons. These are different states of a synapse. And we can consider a general model. So we'll have m different states. And we will consider a model where we have a potentiation with some probabilities that I'm going to denote by f plus, and depression with some probability that I'm going to denote by f minus, and some probability of no change with a probability 1 minus f plus minus f minus. So this is now our model for the single synapse. So this is no longer Hopfield. So now when we want to ask the question of when will the memory pattern be completely forgotten, or put differently, when will there still be a signal in the activity of the synapses, signal in this sense, what do we need to do? What we need to do is to compute this value after I don't know, p presentations of memories, or after p transitions of this type. Now, we already know that in order to compute the state of the network, what we need to do is to, well, let's call this p. So what would be the state of the network after presentation of p patterns, p memory patterns? Well, this would be equal to the initial state of the network multiplied by m to the power of p, where m is the transition matrix. Now, the transition matrix is given by this model. So what we need to do is to explicitly write this transition matrix and then compute what? What do we need to compute? What is the relevant property in the transition matrix? Eigenvalues. We need to find the eigenvalues. So we all know that this transition matrix has one eigenvalue that is equal to 1, which corresponds to one eigenvector whose, and what's the interpretation of this eigenvector? This would be the stationary distribution. Now, if the dynamics converge to the stationary distribution, it implies that all information was lost. So what we're interested in is how fast the dynamics converge to the stationary distribution. And this is given by all other eigenvalues. And most relevant, perhaps, is the largest eigenvalue. The largest eigenvalue will determine the slowest time scale of the dynamics. So we're interested in the largest eigenvalue of this transition matrix, the largest non-1 eigenvalue of this transition matrix. Questions? Is it clear? Questions?
Why should it be the larger eigenvalue?
Why should it be the larger eigenvalue? Okay, so why are we interested in the second largest eigenvalue and not all eigenvalues? So the reason is the following. This is so in general, the state or the probability distribution would be a sum of eigenvectors or sum of projections on eigenvectors, each one weighted by lambda to the power of p. If you're interested in the question of when will we lose some information, then you are interested in the smallest eigenvalue. This will determine the fastest phase of memory loss. But in general, you'd expect that this quantity will have a projection on all eigenvectors. Now, some of the projections will decay slower, and some of the projections will decay faster. Now, if the question that you ask is when will I have some information about the state, then it is sufficient to look at the slower. If we are interested in the question when will I have all the information, you are interested in the fastest. So how does this transition matrix look like? So this would be a large matrix where we don't know whether it's large or not. This will depend on M. It will be an M by M matrix. What can we say about the diagonal terms? What do the diagonal terms denote in this transition matrix? The probability of staying in the same state. So what's the value of the diagonal elements? The value of the diagonal elements would be 1 minus f plus minus f minus. This is the probability of staying in the same state. What about the elements above the element above the diagonal? So this would be corresponds to the probability of moving up or down? Down. This is the probability of moving down. What's the probability of moving down? F minus. And below the diagonal element will be F plus. What about above and below? This will be all zeros. So this is how the transition matrix looks like. This description is almost complete except for one thing that I didn't fully describe, which is what will happen here. What happens when you reach, I'm sorry? Well, this is one synapse. We're talking about a single synapse, not about the memory. But I need to define a rule of what do I do here when I need to potentiate, or what do I do here when I need to depress. Now that, I mean, in modeling work, you can do whatever you want. When we're talking about reality, it makes sense, I think, to use something that is called hard bounds. So hard bounds would correspond to the case in which when you need to potentiate and you are at positive saturation, you just stay. And when you need to depress and you are in a negative saturation or the most left-hand side saturation, then you also don't change. So this would correspond to hard bounds. It turns out that often, well, at least in this paper of Larry Abbott and Stefani Fuzzi, what they did was to use soft bounds. And soft bounds look something like this: 1 minus f plus plus f minus. This is same diagonal, and here they have f minus plus f plus, and same thing here, where they have f minus plus f plus. So the idea is that if you need to potentiate from here, you actually depress. So there's no good motivation to use it except for saying that if you do this, you can analytically compute the eigenvalues of this transition matrix. Now, if you think about a large, if M is large, then we don't expect that behavior will strongly depend on the rule in these bounds, because you rarely meet these bounds. So this is what they did. So this is called soft bounds. And if one is unhappy about this assumption, one can always numerically compute the eigenvalues, assuming hard bound. And actually, they did it and compared it to the eigenvalues assuming soft bound. And when M is large, the results are comparable. Questions? Questions? So this is a matrix that has a particular structure, and it turns out, as I said, that this matrix, the eigenvalues of this matrix can be computed analytically, and I'm not going to do it. If you are interested, the calculation is in the supplementary of that paper of Abbott and Fuzzi, and I'll just give you the results. So one eigenvalue, which you already know, what will be 1. This is a transition matrix, so we know that one eigenvalue has to be equal to 1. There is another eigenvalue, which is equal to 1 minus 2 times f plus plus f minus. And all other eigenvalues have a particular structure, which is equal to 1 minus 2 f plus I think that there is a mistake in my notations. No. One minus 2 f plus plus f minus plus 2 square root of the product of f plus times f minus times cosine k minus 2 times pi over m at minus 1, and this is for all k larger than 2. So the details are not that important, but given that we have an analytical solution, we can now as I said, we are interested in the limit of large m, so the number of states is large, not as large as the number of neurons in the network, but can be, I don't know, 50 or 100, I don't know, maybe 10. And it turns out that lambda 3, the third eigenvalue, is the largest, and in this limit, it is approximately equal to 1 minus square root of f plus minus square root of f minus square minus square root of the product of f plus f minus pi squared over m squared. And I'm not going to prove it. This is just a Taylor expansion in the limit of large m. So now we have an analytical solution to the the eigenvalues of this transition matrix. And remember, we want lambda 3 to be as large as possible. So one thing that we immediately learn from this analysis is that f plus should be equal to f minus. So memory capacity will be largest if f plus is equal to f minus. Because if f plus is equal to f minus, then this term goes away. What is the intuition behind this result? What's the intuition behind this result? Okay, let's say that f plus is larger than f minus. So if f plus is larger than f minus, then we expect that on average, things will go to the positive saturation. And if f minus is larger than f plus, then everything will go to the negative saturation. How long will it take for information to be lost? How long will it take? I'm sorry? Well, how many memory patterns do you think that you will be able to store in this case? So let's say that there was so the question that we ask ourselves is, when will information about potentiation or depression of a synapse be lost? So let's say that we are somewhere in the middle, and there was a potentiation in one case, or we're somewhere in the middle and there was a depression in some case. So in one case, a synapse, or the state of a synapse, is here, and in the other case, in case 1 it is here, in case 2 it is here. Now, we expect that after F plus, so the probability of moving to the right is F plus minus F minus. Now if there are M, so let's say that there are something like M over 2 steps to go to saturation. We will reach saturation after, in the first case, we will reach saturation after M over 2 divided by F plus minus F minus. And in the second case, we will reach saturation after two more states. So overall, we expect that after something that is on the order of M over F plus minus F minus, there will be saturation, or the system will saturate independently of potentiation or depression. So independently of whether we potentiated or depressed, after something on the order of M over this difference, which is something that is, if everything here is order 1, this will be after order 1 steps, all information will be lost. In fact, it is even worse, because if there is a bias, then we start very close to saturation, because all synapses are already very close to saturation. So we expect that if F plus minus F minus, if F plus is different from F minus, then the number of memory patterns that can be stored will be very small, because after a small number of steps, the state of all synapses will be close to saturation, independently of whether they potentiated or depressed for a particular memory pattern. And we see it here in the fact that lambda 3 is strongly dependent on this difference. The place where M contributes is in this term. But if F plus is equal to F minus, then lambda 3 is dominated by this term that becomes closer to 1 as the larger M is, the larger the number of states is. So we will consider this case in which F plus is equal to F minus. Questions? Okay, so what do we need to do now? How are we going to proceed from this point? So we learned something. We learned that F plus should be equal to F minus, and in retrospect we understand why. But still, we would like to know how many memory patterns can be stored and how this result depends on the value of M. How should we proceed? Let's take a break and continue after the break. כן.
כמה F+ ו-F- הם קרובים ל-1?
לא, זה...
אם הם גם שתיהם מאוד קטנים, גם זה ייקח הרבה יותר זמן לא להגיע לסטורציה, כי הרבה יותר מפעים.
אבל מה שחשוב זה, אם שניהם קטנים, אז גם ההפרש ביניהם יהיה קטן. לא, אמרנו שאלתי על הופפילד במקרה של פי שווה 1. מכניס תבנית אחת. עכשיו, מה יקרה כשאתה מכניס עוד? הכנסת, אז אחרי תבנית אחת יש לך סיגנל שהוא 1 חלקי n. מה יקרה עכשיו? אז הסיגנל יתווסף לו כל צד, יתווסף לו רעש. באופן אקראי, חלק מהסינפסות יעברו potentiation, חלק יעברו depression, אז כאילו אתה מוסיף רעש. לא, הוא לא אומר לך שום דבר על תבנית פעילות של התאים. הוא רק אומר, האם יש בסינפסות, זה מדד להאם יש בסינפסות אינפורמציה על זה שעשית פעם, שהכנסת פעם זיכרון. זה לא אומר שתוכל לעשות retrieval. זה תנאי הכרחי, אבל לא מספיק. זה המשמעות של זה, אני פשוט מפרק את הסכום הזה. יכול לחשוב על, אם תיקח את זה ותוסיף הרבה תבניות, תקבל את זה. כי כל פעם אתה מוסיף חלקי n, pi mu, pj mu. זה וזה, זה אותו דבר. פשוט צורה אחרת להסתכל על זה, זה צורה להסתכל על איזושהי sequential, זה צורה להסתכל שהיא לא sequential.
paper by Analytical Solution, do they consider also gems that are not from contiguous states, but from constraint, I don't know, m to n plus 2 or n plus 3, depending on, I don't know, the strength of well, different gems, not
So one thing that Fusi also Abbott worked for quite some time is about different structure, power law.
yes, additive, multiplicative, and power.
No, the idea is that you have more sophisticated rules for transitions. So the idea is that there is some distribution on these probabilities. Paper is called power power law or something. It's another natural science of refining.
And there's like a decay invariance property that
A cascade model of synaptically stored memories. So the idea is, can you do better with more sophisticated transitions? And there's also a paper by, I don't know if it came out, I think it came out, Surya and Guli. So he's asking a related question of, given the complexity of, the idea is that you have different transitions in different, so the idea that the synapse will have many internal states. And this would result in more complicated dynamics of weights.
for single synapses.
For single
And
synapses.
I guess there can also be correlated on behalf of like homeostatic principle that would
All these things are will only add noise.
correlation between
Well, it depends. It depends what you're doing with these correlations. But homeostatic, anything that is activity independent will add noise. So if the synapses constantly change in the absence of memory patterns, then clearly this reduces capacity. The issue of correlation is a different issue. Yeah, but the issue of correlation is a different issue. So on one hand, it's detrimental to most of these models as written this way, but you can decorrelate. There are ways of doing it either by, you can say, well, the network decorrelates the patterns before storage, or you can add the decorrelation into the plasticity. And then, in fact, the capacity can become much larger. Not much. The capacity can go up to 2n. Because then you don't have the interference. As long as so the problem, the interference, the problem is where the reason that other memory patterns interfere in the Hockey model is because the GIJ has two components, so the GIJ associated with a particular memory pattern and with all others. So you could write GIJ as the
others. In all others, you have a signal. Now, if PJ mu and PJ1 are uncorrelated, then the product, sum over J of PJ mu times PJ1 will be 0, and then you have no interference, so there's no problem. You can only do it for n memory patterns, but then you have to have correlation. So this will increase the capacity. Another way of introducing correlation, but in a different way, would be to make the memories sparse. Sparse memories are correlated. Usually 0. But then there's less information within each memory pattern. So the capacity you can have a very large capacity, as we showed when we were talking about Eigenvalues.
כמו שאת אומרת, כאילו, זה מההיכרות, זה לא מהמשקע. לא, אני מצאתי, זה אני מצליח
גדול.
אני לא.
סיגנל תנועה זה היה n חלקי p. שורש n חלקי p. שזה גדול. או אצלי. יכול להיות שזה אצלי. צריך להיות נוט של הוקפילד. השיטה של הלקצ'ר נוט על הפרק של הוקפילד עכשיו. גם שם יש טעות.
באמת יוצא אוקיי, כל סליחה אולי כאילו נגיד אחד עוד שוב זה עכשיו לטייל נגיד עושים שיעורים לא יודע אם נורמלי אבל כן, זה בתים, זה הרבה בתים זה דירה שאני שם וכבר זה תקופה טובה מאוד בסיום מאוד לא, כי נורא זה בטח
Okay, so we have our synapse, or our population of synapses, and there is a rule that every time that there's a new memory pattern, there's either potentiation or depression with some probability, and we concluded that this probability should be the same for all for potentiation and depression, otherwise we will reach saturation too quickly. Now the requirement is that, or a necessary condition for a memory to be maintained is that this signal will remain large. Large compared to chance. So what would be the magnitude of chance here? How are we going to compute the magnitude of chance here? So we need to look at this quantity. We need to look at this quantity when we when we randomly choose synapses to be potentiated as if they are potentiated and depressed. So the magnitude, this, in order for this for signal to be maintained in the system, this should be large compared to a random subset of synapses. So what would be the value of this if rather than choosing the particular synapses that were potentiated and depressed, we randomly choose a subset of synapses, the same number of synapses to be potentiated or depressed. So to compute this, what we need to compute is the variance of 1 over n, sum over I, wi, where these would be n times f randomly selected, minus sum over j, so we can write I being equal to 1 to n over times f, j equal to 1 from 1 to n times f randomly selected, randomly selected. So this is a measure, the term here is a measure of what we would expect by chance. So we need the signal to be larger than what we expect by chance, which is just equal to 1 over n squared from this n times 2 nf, the variance of a single synapse W. Which is equal to 2 f over n variance of W. So the requirement is that the signal after P memory patterns over the noise should be much larger than 1. The signal to noise should be much larger than 1, and this would be, let's call it T is equal to P. So this is, after presenting P memory patterns, we still want a signal over the noise to be larger than 1. If it's not larger than 1, then it implies that the information is lost. Or we can say that the requirement is that the signal over square root of f over n should be much larger than 1. We said that W is between 0 and 1, so its variance will be order 1, and 2 is order 1. So we can remove all the order 1 terms and require that the signal to noise is larger, should be larger than 1. Questions? So what is the signal? Well, the signal at time t is equal to p is something like the signal at time 0 times lambda 3 to the power of p. Why do I say it's not exactly equal? Why is it not exactly equal? I'm sorry? Because what we really need to do, you're absolutely right, what we really need to do is to consider the projection of this signal over all the eigenvectors and consider all other values, all the eigenvalues. This is what we need to do in order for this equality to be correct. So there's a cheating here, because it's not really equal to. But the idea is the following. The idea is that there will be an order 1 projection over the largest eigenvector, and that when p is large, this eigenvalue will dominate. So there will be a prefactor. There will be a prefactor resulting from the fact that there is a projection, that we need to consider the projection on the eigenvector. So this is one thing that is inaccurate here. And the second thing, that we need to take all other eigenvalues. So there are two cheating is introduced in two ways. One, we need to consider the projection on the eigenvector. And second is that we need to consider all other eigenvalues. So there are two sources of cheating here. Again, one, that we need to consider the projection on the eigenvector, and the second, that we need to consider all other eigenvalues. But so the second one will disappear or will be dominated by this one in the limit of large P. And this will add an order 1 correction. So we don't care about it. So this would be equal to the signal at time 0 times one minus f pi squared over m squared to the power of p. This is from this term, and we assume that f plus is equal to f minus is equal to f. So we use the usual trick. This is st is equal to 0, and then we write it as e to the power of log 1 minus f pi squared over m squared to the power of p. And in the limit of large M, log of this f times pi squared over m squared is small, so 1 minus so the log of 1 minus epsilon is approximately equal to minus epsilon. So this will be equal to s of at time 0 times e to the minus p times f pi squared over m squared. So what we did here was to take the large m limit. So now the requirement is that s at time 0 e to the minus p f pi squared over m squared divided by square root of f over n should be much larger than 1. And this implies that p should be smaller than m squared over pi squared f times log of s0 over square root of f plus half log n. If I'm not mistaken. So what do we learn from this expression? So it's composed of two terms. Let's talk about the first term. So the question is, well, we know everything except for s0. Let's say that f is 0.1, or maybe f is 0.01. Let's say that f is an order 1, that f is order 1. If f is order 1, then going back to S0, this is the magnitude of potentiation and depression, then we expect that a finite number or a finite fraction of the network will be potentiated, and a finite fraction of the network will be depressed. So the magnitude of S0 will be something like 1 over m multiplied by s or something like this. So S0 will be something like 1 over m. So altogether, this is an order 1. This would be an order 1 term. This is a term that will not depend on the number of neurons in the network. Now, the place that the number of neurons in the network enter is where? In n. What is n? N is n squared. So this would be equal to m squared divided by pi squared f times this order 1 term. Let's leave it as is. Log of S0 over square root of f plus half of log n squared, which is log n. So if f is order 1, then S0 will be order 1. So S0 over square root of f is order 1. So this entire term is order 1. So P should be smaller than m squared times log n. So remember, the capacity in the Hopfield model was n. Now the capacity is reduced to log n times a correction which will depend on the number of states, square of the number of states of the synapse. So the effect of taking bounded synapses, is substantial. Capacity goes down from being order n to be limited by order of log n. Now, even if the number of neurons in the network is large, log n is still a small number. I mean, imagine that we have, I don't know, take your favorite cortical region. You can have 1 million neurons or 1 billion neurons. Still, the logarithm of n is small. So this is a substantial issue. So we were very permissive in our signal term. We didn't say how from this signal term memory patterns can be reconstructed. This is a necessary, not a sufficient condition. Nevertheless, just by assuming that the synapse is bounded, the result of this assumption is that the capacity should be not order n, but order log n. So this is something that has puzzled computational neuroscientists since the 1990s. This is a serious issue. So how are we going to correct for it? What are the possible solutions? I'm sorry?
Increase the state in the synapse.
The question is, what's the approach? So, I mean, you're right that the larger the number of states, the more capacity, the larger will be the capacity. I completely agree, but we are not constructing brains. We're trying to explain brains. So we are unable, I mean, we're thinking about the synapse as a biophysical entity. It's difficult to imagine how a synapse can be continuous. Now, even if a synapse is continuous, then you can think about these, the discretization as a way of accounting for noise in the system. We're talking about molecules. First, number of molecules is finite, or number of receptors is finite, number of vesicles is finite. But even if we think about it as something that is close to being a continuous system, this discretization is a way of accounting for possible noise. So even if the synapse is continuous, still the fidelity of a synapse is finite. And how many different states can you have? One? Well, one is not sure. Clearly no. 2, 50, 100. Clearly not more than that. So people have tried to account to address this problem in various ways. One is to consider more sophisticated structures of synapses that have many internal states, and if you construct internal states in a smart way, then one can increase the capacity somewhat. That's one way, and two recent papers. One is another paper by Stefano Fusi and Larry Abbott, and another paper by I think it's out. I'm not 100% sure that it has been published. Another one by Surya Ganguly from Stanford. They have studied how complicated synapses can result in a higher capacity. That's one approach. Another approach is to look at this term and to look at the whole thing and ask how small can f be? And you have a three-factor f here. So the smaller f is, the larger is the capacity. So it seems that the optimal thing would be to take f to be equal to 0, right? If f is equal to 0, then the capacity is infinite. But of course, this will not work, because if f is 0, then the signal becomes 0. We assume that this is order 1. The assumption that this is order 1 was based on the assumption that f is order 1. If we take f to be equal to 0, then this term, the signal will become 0, and this will become minus infinity. So this term will kill this term, this log n term. So we cannot take, and also it doesn't make sense, right? If f is equal to 0, then you don't do anything. There's no change. So clearly, you can't encode many memories by not doing anything. So you cannot take f to be equal to 0. But if you carefully fine-tune f and take f to be small enough, one can increase the capacity from being order log n, as it is here, to bring it up to a square root of n. Square root of n is much smaller than n, but much larger than log n. And people have studied or proposed that maybe f is very small. And in this case, even if synapses are binary, if the probability of a change is sufficiently small, then one can reach a square root of n capacity. So that's one kind of a solution. More questions?
The first option was changing this transition matrix.
Constructing, yes, a more sophisticated transition matrix in which some synapses change fast and some synapses, as a result of being in different internal states, in some synapses this probability of transition is large, and in other synapses the probability of transition is low. Now, if you want to think about it in an intuitive way, I mean, imagine that for every memory pattern, you consider only a small subset of synapses and make changes only to these synapses. So then capacity is much larger. So you assign this group of synapses to memory 1, this one to memory 2, this one to memory 3, and so on and so forth. Then the capacities can become larger. So the way that they incorporate this idea in a more realistic framework is to say that synapses have different internal states, such that at any point in time, some synapses are more likely to make changes than others, resulting in a larger capacity. But this requires a particular this requires that the biophysics of the synapse would somehow be tuned to these multiple timescales in the encoding of memory. Even this simple model requires fine-tuning here. Now imagine that f plus and f minus are not the same, are only approximately the same. Then again, the capacity becomes order 1, as we saw in the standard Hopfield model. So to conclude this and the previous analysis, we have an interesting framework for the encoding of memories in a distributed way. But there are issues. There are issues that have not yet been resolved. One of them is the issue of fine-tuning that keeps on appearing whenever we try to do something interesting with the brain, with this framework. framework of the brain. Questions? So if there are no additional questions, I would like to go back to the Hopfield model and point out some additional points that I wanted to that I think are important, and the topic would be random networks. So the Hopfield model, Jij was equal to 1 over n, sum over mu, pi mu, pj mu. So the first question is, how are the synapses distributed in the Hopfield model? So for example, what would be the average of Jij? What can we say about the distribution of synaptic efficacies? Let's say that I'm interested in a particular synaptic efficacy. So particular synaptic efficacy is a sum of many independent terms. So how will it be distributed? So we expect the Jij to be normally distributed because of the central limit theorem, with a mean of 0 and variance what would be the variance? So we have 1 over n squared here, right? Times p elements, each one is plus minus 1 with a probability half. So the variance of each element is 1. They are all independent. There are p such elements. So the variance would be p over n squared. So the Jij is normally distributed with mean 0 and variance which is p over n squared. So a fair question to ask would be, do we expect a model in which Jij is normally distributed with a 0 mean and some variance, this variance, to behave exactly as a Hopfield model behaves? Or what's the difference? What are the fundamental differences between this model and a model that is defined this way? Are there any differences between this model and this model? Or are we talking about the same model? Is the question clear? I will repeat it. So we went back to the Hopfield model, and now we are considering individual synapses. And a straightforward calculation resulted in the result of a straightforward calculation is that in the Hopfield model the synapses are normally distributed, with a zero mean and some variance. So the question that I'm asking is, if we take a model in which synapses are distributed from a normal distribution with a zero mean and some variance, will the behavior of the model be similar or different from the Hopfield model? What are the differences between this model, a model that synapses are distributed this way, and this model? Now remember, pi and pi mu, pj mu are random numbers. Now there are two fundamental differences between this model and this model. What are these fundamental differences? Well, this would be the outcome of a behavior, but just talking about the definition of the model. Is this model equal to this model? I'd like to argue that it's not. It's not in two very important ways. One is in the Hopfield model, Jij is equal to Jji. There is symmetry in the Hopfield model. If we define such a model, then there's no guarantee that Jij will be equal to Jji. In general, it will not. So this model is not equal to this model. First, because Jij is equal to Ji in the Hopfield model, but not in this model. Now, why do we care about it so much? Okay, whatever. Why is it an important property, this symmetry? Sorry? Why is it important? Stability. What do we know? What do we know about matrices that are symmetric? We know that the dynamics will necessarily converge to a fixed point. This is not necessarily the case here. There's another fundamental difference, and this has to do with the structure of the matrix, or the rank of the matrix. So in the Hopfield model, J can be written using matrix notation as a sum of P vectors times the transpose of these vectors. This implies that the rank of the matrix J, if P is smaller than N, if the number of memory patterns is smaller than N, and this is the regime that we were considering, the rank of J will be equal to P, because these vectors are almost orthogonal. So the rank of the matrix, is much smaller than the rank of this matrix, which in general be N, even if we take Jij to be equal to Jji. So there are two fundamental differences between this model and the Hopfield model. One is the symmetry, and the other one is the fact that the rank of the connectivity matrix will, in the regime that we considered, will be smaller than the full rank, implying that there are correlations in the connectivity matrix. So this is not, despite the fact that in the Hopfield model Jij is normally distributed, this model is different from this. Hopfield model is different from this model because there are correlations, and these correlations play an important role. with these two observations, now it will be interesting to ask in what ways will the Hopfield model, the behavior of the Hopfield model differ from the behavior of this model? And we can ask questions. Okay, let's consider a model where synapses are normally distributed while complying with symmetry but not with this. This is kind of a question that we can ask ourselves. By the way, how are synapses in the brain distributed? Does anyone know? Yes? So it turns out that if you look at the distribution of synaptic efficacies in the brain, the distribution is very close to log normal. So the logarithm of synaptic efficacy is normally distributed, which is kind of interesting. It's interesting because, well, a normal distribution naturally emerges if we sum many independent variables. How would the log normal distribution emerge? So a normal distribution is something naturally emerges because of the central limit theorem from summing a large number of events. So you can imagine, just forget about Hopfield, you can imagine some synaptic plasticity rule events that are taking place are all random and independent. Every event has an additive effect on the synaptic connection. Then we would expect that the distribution of connections would be normal. What can underlie log normal distribution?
Certain synaptic efficacy, the basic one, and from the other synapses are power of that synapse.
I'm sorry?
That it's discrete, I guess, the synapses with the log.
So okay, so maybe I will say a few words about how synaptic efficacy, how the strength of synaptic efficacies is measured. So there are two. I would say that there are two ways of doing it. One is to do very tedious experiments in which you take a slice and you patch several neurons in the slice, and you inject current in one and measure the EPSP or IPSP. You measure the response in other neurons, and sometimes the neuron is not connected, or the pair that you're considering is not connected, and then there's nothing you can do about it. But if you find a connected pair, you can measure by how much will the membrane potential in one cell change as a result of an action potential in another cell. And in order to increase the efficiency of this tedious process, what people do is patch 4 neurons or 6 neurons and measure these EPSPs, and then they do it for like, I don't know, 1,000 pairs, and then they plot the distribution of EPSPs. This is one way of measuring it, and it looks something like this. So this would be the number of events, and this would be the magnitude of EPSP, and let's say that this would be, I don't know, 1 millivolt, depending on when you where you do it. The first one to do it was Sen Song. Well, he was the first one to analyze it, analyzing data collected in the lab of Sasha Nelson, and this is what he found. This is quite a lot of work. So this is distribution, and then rather than looking at the distribution of EPSP, what you do is you look at the distribution of log EPSP. and then you get something that looks very nice, very normally distributed. So this is one way of measuring synaptic efficacies in the brain. There's another way, which is easier, and I told you about spines when we talked about learning experiments on spines. Now there's evidence that the size of a spine is approximately proportional to the efficacy of a synapse that reside on it. So what one can do is one can measure, one can take many spines and look at the volume and compute the distribution of the volumes of the spines or the log of the volume of the spines, and you get basically the same results. So it seems that the distribution of efficacies in the brain is not normal, but log normal. And so a normal distribution is the result of, if the synaptic efficacy is the result of many independent events, then we expect that W would be normally distributed. If log W is a sum of many events, then we can say that W, let's call it J, right? We're using J for efficacies. Then we expect that the efficacy will go like the exponent of sum of Zi, which is equal to the product of e to the power of Zi. So if a normal distribution naturally emerges from a sum of many stochastic variables, a log normal distribution naturally emerges from a product of many stochastic variables. Why should synaptic changes in the brain be something like a product? It's not known. So there are two interpretations. You have a question? Okay. So one is to say, well, we don't know. It looks like a product, but we don't understand why. And actually, if you look at the dynamics of sizes, at least in the case of spines, the dynamics of sizes of spines is something that changes that looks like the changes in sizes of spines seem to be multiplicative, at least in the auditory cortex. So this is consistent with emergence of log normal distribution. There's another interpretation, however, that I have to tell you, should tell you, and this is the following. So some people say that this observed distribution is actually an artifact of the measurement. It's very difficult to measure small